This video concentrates on factoring when the lead coefficient is not 1. Okay, just to let you know, this AC method of factoring, which is what I've come to know this as being, is different. I don't fully understand why it works, and because of that, I don't feel comfortable teaching it very well. And I'm sure that looking back at proofs, like for instance the one that I have here in my disclaimer, that if you go to this URL at mathforum.org, I don't remember his name, but the Dr. Math that is posting on that does a pretty good job, I think, in explaining it. It's just a matter of I don't see it, and so I'm just gonna kind of go with it for right now. I see the proof. I don't see any mistakes, and so I'm just gonna go ahead and assume that he's right and that this works. And to some extent, I see that it does. I did find one instance where if you're not careful, it doesn't work, but it would kind of fake you into thinking it does. And I'll cover that at the end. Okay, so here's the method. And the first thing, you have to assume that you have a quadratic expression or an equation in the standard or general form. Okay, and so standard or general form is simply in the form of ax squared plus bx plus c, for a, b, and c. In the case of this level that I'm kind of putting this video towards, they're all integers. Okay, they can be anything really, but right now we're just going to assume that they're integers. They can be negative, so be careful on the signs. Now, as just a small point, for those of you that are unfamiliar with perhaps later quadratics, they aren't restricted to things that only have x squareds. You can actually have one that looks like this: x to the 4th plus bx squared plus c. As long as the exponents on the x's, as long as that lead exponent is in fact double that of the next term. So if the degrees of the first term are double that of the degree of the second term, you can go ahead and use this method. I have not checked on multivariates. I'm going to just assume at this point that it will work for multivariate as well. Multivariate meaning that you have x's and y's. Okay, and I'll go through one as an example. I'll try anyway in my next video to go through one that has multiple variables in it, so that we can see how that plays out as well. Okay, so let's go ahead and start. Now, we need something to work with this. I'm going to try to do one kind of parallel to everything. So I'm just going to go ahead and give you one here that I've already done up. And that one is 6x squared plus 17x plus 12. Okay, and this is just as an example to show you how this method works with a particular example rather than in a general sense. So we have x squared. Now this first thing says remove the leading coefficient a and multiply it with the constant coefficient c. In other words, we're going to take this first number and we're going to multiply it to this last number, and then we're going to go ahead and put that at the end as a quote new last number. So I have x squared plus 17x. 6 and 12 is 72 for multiplying. Now this kind of illustrates a point I was trying to make earlier, or I was going to make earlier, but I'd wait for it. Notice how this number is, I got two relatively small numbers, 6 and 12, but when I multiply them, I get numbers that are pretty big. You can get well into the hundreds on these if you're not careful, so there might be another method out there better for that particular instance. And in fact, I do have another one that I'll have a video on. Okay, now, so we've got part 1, step 1, remove the leading coefficient a and multiply it with the constant coefficient c, 6 times 12. Put the product as the quote new constant coefficient and remove it. Okay, like I said, remove that leading term. It's no longer there. Now, step number 2. We're going to factor the resultant quadratic as we would if we were just dealing with any other quadratic with lead coefficient of 1. And then find the factors. So you're going to find the factors of 72 in this case that will add, and my students are aware of this, and I have videos on that as well. I always do these signs separately, and we talk about how we derive those signs. But I do the signs separate. In this case, we need two factors of 72 that add according to the second set, that add together to make 17. And when we do that, we find out that, well, if I look at 8 and 9, 8 plus 9 is 17. Okay, we're done. Sweet. All right, so we factored that. So we're going to factor this into x plus 8 and x plus 9. So we have factored this example from step 1 into this form for step 2. Now step 3 has us rewrite our step 2, and it says replace A. Now remember, A was this magical thing out in front. And so in our particular example, it was 6. So we're going to put 6 back into the leading coefficient spot, into that where it normally would sit for both factors. And so this becomes 6x plus 8 times 6x plus 9. Now, this is one of those tricks, one of these things that I don't like. I just flat out don't like it when I don't understand what's going on. And this is a step where it's just, it just nags at me. But again, Dr. Math explains it, and I accept it. I don't see any particular flaws in the logic that is given. It's just hard to wrap my head around. Some of you might look at this and go, oh, well, duh, it makes complete sense. All right, well, obviously you're a lot smarter than I am, which is really, sorry, but it's really not hard to do. Okay. All right, so we've got step 3. Step 4 says factor out the greatest common factor of each of the factors. We have to be careful here. Both factors, 1, 2, 2 factors, 2 greatest common factors. Greatest common factor out of 6 and 8 is 2. So we have 2, and then we'll have 3x plus 4. Greatest common factor out of 6 and 9 is 3, and so we'll put a 3 kind of just out in front of it and say it's 3, and it goes 2x plus 3. Okay. And in my explanation of the general sense, I'm going to assume that A divides M evenly. And actually, in this case, it divided both M and N, the 2 factors that I had. All this is saying is that M is a multiple of A. And in this case, 8 was a multiple of 6, but it's not really. It doesn't have to be a multiple. Okay, so finally, step 5, drop any greatest common factors from step 4. And by drop, they literally mean drop. Just eliminate them as if they weren't even there. And rewrite what's left. And if you do this, this is supposed to be your answer. And if we want to check this just with our particular example, let's go ahead and multiply it through using the distributive property, not that godforsaken 4-letter F word. And so we're going to distribute 3x to both the 2x and the 3 to get 6x squared plus 9x. Then we have 4 times 2 and 4 times 3 for plus 8x plus 12. If we combine like terms, 6x squared plus 17x plus 12. And if we scroll up, we will see that that's exactly what we started with. Okay, so the method, at least for this particular problem, looks like it works. And as you go through, and I encourage you, go to that website and look through that proof. If you look through the proof, he does all of these things. He just does them in variable form. And there are certain assumptions that he has to make, and that's fine. It's a little bit of a difficult read, at least for me, but I think it's well worth it. You see that this isn't just magic; it actually works. How it works looks like magic, though. And so again, I put down this warning. I don't like to teach or advocate for methods that I don't particularly understand well. And certain people love this method. I don't. The numbers get too big, too easy. And so I have a slightly different method. And I have a video on that as well.